All right, yeah, thank you very much, Will, for organising this. Thanks you guys for all coming to join me for my flag science. This is the second instalment of Dr. Jackson. So it should be, you know, getting a little bit good by hopefully. So basically, I challenge myself to try and teach people, you know, kids, the elderly, adults in between, everyone, about like really complicated topics in space without using complicated language, without using difficult equations, without using numbers, without even really using words on the slides that I show sometimes. So this is really something that I can learn about as well. So at the end of my presentation, if you guys have any suggestions for me or comments about how you think I could maybe do better for this presentation, then please let me know. I'd really like to hear. What is the sun? Well, it's a star, we know that. Do we know what the sun is made of? Well, it's made of this stuff called plasma. And some of you might be familiar, hopefully most of you are familiar with the idea that we have solids, we have liquids, and we have gases. But in actual fact, there's another thing on top of this called plasma, which is what the sun is made of. Plasma is really similar to a gas, except it's got a couple of differences. One main difference is that it's electric, it's magnetic. Magnetic fields can't move differently from this. I don't know whether you guys have ever played with iron filings and things like that, but if you have, when you move a magnet close towards, oh, I can't turn the screen sharing off now. This is, okay, anyway. So when you move a magnet close towards iron filings, you always see these kind of patterns of the magnetic field lines taking place. And it's the same kind of way that plasma works. So what are we looking at when we look at this? Let's share my screen again. So what are we looking at here? I said we're looking at a ball of plasma, but it's very interesting. It's not actually a ball like a football or like the Earth. In fact, there's not really a solid surface to this. The plasma that the sun is made of, this gassy stuff, comes all the way out to Earth. But what happens at this point, the point that we're looking at, this ball, this is where the density of the plasma, so that's how much stuff is crammed in, when that gets low enough so that light can escape, that's what we're actually seeing. So that's what I mean when I say the surface of the sun. It's not like a proper surface like when we talk about the things like that. Now I said when light can escape. Oh, is that a question or am I just hearing a lot of feedback? Okay, feedback. It is. Cool. So I said that this is when light can escape, but there are different types of light, right? Have you guys ever heard of this? I'm gonna assume that you're kind of aware that there's different types of light. And there's actually different wavelengths of light, we say, because light can be thought of as a wave. So on the left here, you've got red, which has got a very long wavelength. And on the right, you've got the violet, which is a very short wavelength. But there's even more light which we can't see. For example, you might have heard of X-rays, you might have heard of gamma rays, microwaves, infrared, radio waves. These are all the same kind of thing. They're all light, electromagnetic radiation. But it's just this visible bit is a very, very, very tiny part of the spectrum. So when we look at the sun in this visible light, I mean, I'm a solar physicist, and even I think this looks kind of boring, right? There are some spots here, which I'll come back to in a minute, but for the most part, it's, you know, it's a pretty plain experience. But what about if we were to look in some of these other kind of lights? Well, we can develop cameras that can see some of these other lights. For example, if you break your leg and you go to a hospital, a doctor will take a photo of your leg using an X-ray camera. And they'll do that because the X-ray camera shows up bones, but it doesn't show up flesh. So in a similar way, if we point a different camera at the sun, maybe we'll be able to see different things. And here is a mosaic of a few different photographs that we've taken of the sun in a few different lights. And this is really cool. I mean, I know this is my job, so I kind of have to think it's cool, but like, the differences in some of these pictures are incredible. You know, if you look at this yellow one in the middle, you can see some really bright stuff. But then if you look at the green one just above it, it's not quite as many things happening. And then the orange one next to that has got another different sort of structure to it. So there's lots of different things we can see if we look at the sun in different wavelengths of light. And the reason this is important is because the light comes from an atomic process, an atom and an electron recombining and letting out energy. And different types of light come from different types of energy, and well, not different types of energy, different amounts of energy rather. And different amounts of energy means a different temperature. So when we're looking at all these different types of light of the sun, we're actually looking at different temperature plasma of the sun. So now it's starting to get real interesting, and we can maybe actually learn some things about it. But before we start learning, I think you want to see a beautiful movie of this. Hell yeah, you do, because I do. So now we're looking at the same movie, but now we're looking in ultraviolet light. Actually, it's called extreme ultraviolet light, because ultraviolet light is too boring, so we've got to have extreme ultraviolet light. And it is pretty cool. It does look pretty extreme. You know, it's a lot more dynamic. There's a lot more stuff happening. There's bright things. And these bright things line up very closely with the sunspots. So that's interesting. These loops seem to be forming between these sunspots, these patches. Now, normally at this point, I ask if anyone knows what they are, but since your microphones are all muted, I'm just going to get you to shout out, and your teachers can remember who was right and who was wrong. If anyone knows what this is, what these loops come from, you can shout out now. That'll do you. So, I was talking about iron filings earlier, and I was talking about this plasma being unable to move separately from magnetic fields, just like how iron filings are unable to move separately from magnetic fields. This is exactly what it is. There's magnetic fields everywhere in the sun. In the middle is very, very dense and very, like, you could almost think of it as being really heavy gas, like there's so much of it in there, that when it moves, it pulls around the magnetic fields. But up in the solar atmosphere, the point where we're looking now, the plasma isn't very dense, you know, it's almost like air, you know, it blows around very, very easily, but the magnetic fields are still quite strong. So now, the motion is dominated by the magnetic field, and that is why we get these loops. You can almost imagine like a little magnet just underneath the surface, and you would get loops looking very much like this, poking up. Now, the next question is, does this change at all? Do we always have the same number of loops on the sun, or you know, what's going on? And the answer is no, actually. It's very, very interesting. The number of sunspots on the sun goes up and down every 11 years. So this is a bit of a confusing graph to look at first, but if you slow down, you can understand it. Now, on the left-hand side going up, we've got the number of sunspots that you can see on the sun. And on the bottom, we've got time. So you can see as you go through time, you get quite a few sunspots, then it goes down, 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 not very many sunspots. Then it goes up, 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 lots of sunspots, down, 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 not many. And this happens every 11 years. So that's very interesting. The fact that this is so routine and rigid, every 11 years we see a lot of sunspots and then not many sunspots. And actually here is the current cycle that we're in now. And it hasn't been as powerful as the one which we were expecting. There have been a lot fewer sunspots, which is quite interesting. But this is a bit of an aside. This is something that you could maybe look up yourself, the current space weather conditions. So where do these loops come from? I said they're magnetic fields, but magnetic fields don't just suddenly appear out of nowhere, right? I mean, I wish they did. It would be pretty cool, but that's not how the world works. Things don't just happen, you know? They happen for a reason. And you can sort of think of it as being like this. Now, this shows the sun, the orange ball, with magnetic field lines in blue. And this looks a bit like the Earth's magnetic field right now. You know, we've got a strong North Pole, a strong South Pole, and then in between, not really that much happening. But the key for the sun is that it's plasma. It's not solid like the Earth. So that means that the middle bit moves much faster than the bits at the top. And so this winds up and gets tangled and tangled and tangled. And then all of a sudden, all these twists start poking out like loops, like the loops we see. And then after 11 years, the bottom loop will reconnect with the top loop and they'll all ping, 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 ping. Whoops, whoops, back to there. Hey, pretend I didn't do that. Hey, all right. So let's just watch that again. You can see how it pulls these magnetic fields round and round, stretches them. They're like rubber bands almost, you know. You can imagine them really twisting and pinging out like that, and then boom, back to the beginning where it repeats again and again. So this is pretty cool. This is certainly pretty cool, but I haven't even got to the part that I study yet. So that's interesting. What I study is the plasma which gets lifted up by these magnetic fields. And that happens like this. So here is a very basic drawing of a sort of bundle of magnetic field lines poking up out of the surface of the sun. The gray is supposed to be this surface of the sun that I was talking about. And so now you can see we've got this big black bundle of magnetic field lines, and there's one red magnetic field line twisting around it. And as this rises up through the solar atmosphere, through above the surface of the sun, it pulls with it material. And this material looks like this. Now, this is one of my absolute favorite movies from the sun. I think it's so beautiful. Just for scale, I think the Earth is about as big as the clock in the bottom left-hand corner. So this is like, it's like a hedge made of fire that's 10 times bigger than the Earth. You know, it's mind-blowing. It's absolutely crazy when you try and think about it like that. And the more I watch this, the more beautiful I think it is. So this is called a prominence, or it's also sometimes called a filament, because sometimes scientists are stupid too. Unfortunately, I hate to admit it, sometimes we are. People saw these things, some people called them filaments, some people called them prominences. They could never agree, so we call them both, which makes total sense. Anyway, sometimes these aren't quite as gentle as the movie that I'm showing here. Sometimes they're a lot more violent, which, you know, you might sort of say, well, come on, Jack, how violent can these things really get? It's just plasma being held up by magnetic fields, right? It's not like magnetic fields suddenly do anything completely crazy. Oh! Yeah, okay, that was a bit of an overreaction. But, right, you remember how small I said the Earth was? I don't know if you can see my mouse, but the Earth is very, very, very small on here. The amount of material which is exploding out is like hundreds and hundreds of times the size of the Earth. This is insane. And what's happening here is at the very beginning of the video, where the explosion comes from, we've got one of these little prominences, one of these little filaments. And it's becoming unstable. The magnetic fields become unstable. And then suddenly this triggers a runaway eruption that throws plasma out into the solar atmosphere in huge amounts. And these are quite common. These tend to happen, you know, once a day. This is a particularly massive one, so we won't see something like this every single day. But you do get a prominence eruption, maybe once a day, maybe once a week. Very, very common. And I can show you some even cooler movies as well, actually. If we zoom out a little bit. So now, this is a bit tricky. We've blocked out the sun because the sun is way too bright to look at in this picture. You know how when you go outside and you want to look at a cloud in the sky, you have to kind of block the sun out of your view because otherwise you just can't see anything else. It's the same thing for this. And so now we're going to see how this solar atmosphere, how this stuff extending upwards away from the sun changes when we see one of these eruptions. We see another bloody huge eruption, you know, shocking, right? You see an eruption down there, you see an eruption up here. You might not be that surprised, but I hope you're still impressed because these are still absolutely stunning, stunning movies, you know. I would tell you how small the Earth is again, but you're probably getting bored of me flogging that dead horse. So this is the first sort of idea of space weather that I want you to think about. These are called coronal mass ejections. From the corona, which is what we call the atmosphere of the sun, so coronal. Mass, because, well, as you can see, there's a lot of material, a lot of matter, a lot of mass being ejected, so coronal mass ejections. These are like big explosions, they're like big storms in space weather, almost. And watch them as they go from the sun to the Earth. So now this is a composite of several different pictures that we've been taking from different cameras. On the left side of the screen, the tiny orange ball is the sun. And on the right side of the screen, you can see the Earth. And you can see at the front of the Earth is light and at the back of the Earth is dark because it's the daytime and the nighttime, depending on whether we're facing the Earth. And now when I play this movie, you should see a couple of CNEs. if you watch closely, there's one, and you can see it move from one camera to the next. So this is very interesting. This is interesting, but also frightening, you know, because it says to me, oh, these CMEs could actually hit us, you know, like, do we need to worry? Is there anything that could potentially happen to us that's like a result of these CMEs? And, right, let me see. Can I see your videos? Right, hands up if you think it will affect Earth. All right, I like it. Hands up if you think it's not a big deal. Okay. So you guys are clearly thinking. I like that. That's good. You already sort of have a rough idea that, well, we might not be in for such a pleasant trip if one of these happens. So can you see the comet in this picture? Because it's very difficult. Hands up if you can. Okay, so one school can see it. Yeah, all right. Okay, good. I think you can all see it. So this is really cool because you see we've got this comet, and it's got a body on the right and it's got this tail on the left. And it's moving towards the right, it's moving towards the sun is to the right. And when I play the video, there's going to be a coronal mass ejection. I just want you to watch what happens to the comet. So if I play it again, hopefully you will all notice that as the CME moves past, it rips the tail off the comet. Like, that's savage, man. Like, it doesn't even hesitate. It just tears it straight off. And the reason this happens is because there's so many magnetic fields in this CME. We sometimes call them magnetic clouds. And the material which makes up a comet's tail is also plasma. And you remember what I've said a couple of times now about plasma and magnetic fields, you know, they can't move differently. So when these magnetic fields come from the right, and sweep over it, it just carries the plasma off with it. And this is why Mars doesn't have an atmosphere anymore, or not much of one at least. Because just over time, more and more CMEs swept past it, taking with it the plasma, stripping its atmosphere away. So pretty crazy. So it turns out that space weather can affect us a little bit. Now, I'm going to ask you again a question, one more. I want you to put your hands up if you think that the Earth is affected in the same way. Couple of people think it is. Okay, so hands up if you think the Earth is affected in a different way. Okay, good. I was just making sure you're all paying attention. I wanted to make sure you all put your hand up for at least one. No, I'm kidding. So, interestingly enough, it would affect the Earth in the same way, but there is a slight difference between the Earth and Mars, and that is this. The Earth has its own magnetic field, and it looks a little bit like this. So Mars is slightly different to the Earth. Mars is actually quite similar to the Moon because it doesn't have a rotating iron core to generate a magnetic field. It doesn't have much atmosphere left because it doesn't have this magnetic field. The Earth and some of the other planets, like Jupiter, have a magnetic field. So this provides a sort of shield towards the solar winds, towards these CMEs that come in. But the cool thing about the Earth's magnetic field is that it doesn't actually look quite the same as a magnet, not like this, because you've got the sun to the left-hand side, and that is constantly pushing out this slow stream of solar wind, we call it, which is another piece of space weather that I haven't mentioned because it's a bit less exciting. It's kind of like talking about a gentle breeze. I'm much more interested in the storms, you know. But this gentle breeze, this solar wind, does affect the Earth's magnetic field like this. It makes it look a bit uneven. It makes it look a bit silly if you ask me, but hey, I'm not a magnetospherics physicist. Now, how do these CMEs interact with this magnetic structure? Because I will give you a clue. You all said that you do think that CMEs will affect Earth, and you were all right, because they do affect the Earth, just not in quite the same way. So what happens is, if we have magnetic fields which are opposite each other, they look like this. If they move together, they can reconnect like this. Now, this is a very, very complicated topic. You know, this is the kind of thing that they really only teach you towards the end of university. So don't worry if you don't understand it. But if you think about this a little bit, you know, we've got these magnetic fields that start off pointing opposite directions. They move together and then sort of snap and reconnect, and then move apart as two new different magnetic field lines. So if we watch a coronal mass ejection come towards the Earth's magnetosphere, you get this reconnection happening at the front. And then this allows these magnetic field lines to be peeled back to the backside of the Earth. Here, they build up and up and up, and then they can reconnect again, bam! And then all of this solar plasma streams down into the Earth's atmosphere. So, pretty interesting. We get this reconnection at the front and reconfiguring of the magnetic field lines, and then this sudden depositing of plasma in the Earth's atmosphere, and that can result to a whole load of different things. Here's just a few examples, you know, like it can cause problems for satellites, it can damage their solar cells, it can cause currents to be generated in the atmosphere, it can cause currents to be generated on Earth, it can cause currents to be generated which cause fires, it can damage transformers. It really, oh, and another big thing it can do, it can mess up GPS. So I don't know if you guys, your parents uses like a sat-nav in their car, but if there's a really strong solar storm, you will probably get lost. So it might not sound so bad for you because you can probably still find your own way home. But for things like oil drilling, really, really high precision GPS is very, very important. So this can actually be quite dangerous. And so this is kind of the end of my serious talk, but I've got a couple of other fun things that I'd like to share with you. For example, a while ago, I was lucky enough to meet the guy who advises the President of the United States about space weather. Now, I know what you're thinking, but I spoke to him before 2017, when it was actually worth informing the President of the United States about space weather. But anyway, he spoke to him, and then the Federal Emergency Management Agency released a statement. They said, "It would appear that during an extreme space weather storm, we may have to resort to messenger pigeons." And he had a good laugh until this guy pointed out to him that actually pigeons find their way using magnetite in their brains, which is just as affected by a geomagnetic storm as anything else. So unfortunately, you're completely wrong. And it turns out people who race pigeons for sport don't do it when there's a magnetic storm, which is crazy to me. I can't believe they even still race pigeons, let alone pay attention to solar storms. So there you go. There's your interesting tidbit for the day. And finally, it's not all bad news. There are some good things that happen from these coronal mass ejections, from these geomagnetic storms, these solar storms that we experience. And you might have seen them before. It's the aurora, the northern lights, the southern lights, aurora borealis. And what this is the solar plasma. As it rushes down these magnetic field lines and hits the atmosphere, it gives lots and lots of energy to the oxygen and the nitrogen in the atmosphere, and those things start to glow because they have so much energy. So if you can see these stripes that are just going up and down in this video here, that is actually the Earth's magnetic field. So, pretty cool. I hope we've all learned something about space weather today. I hope you've all enjoyed my, I don't know how you'd call it really. I can't stop sharing my screen now. Help, Will, help, help. Okay, it's fine. Hey, so thank you very much. And I'm now happy to try and take questions if we've figured out the chat box, or if we can maybe get the microphones to work. I don't know. That is such a good question because I was supposed to say something about it and I didn't. Good one. Excellent. Right. So it does actually. You know what? Real science is done on the whiteboard, so I'm going to answer your questions on here if that's all right. So now we've got the Earth, which is here, and then we've got the magnetic field of the Earth, which goes like this, right? Whoops. Something like that, anyway. And then the CME is coming from here, and they cause all these problems, but then it's really is here, right, that the problems cause. This is where the solar plasma rushes down the field lines. Does that make sense? Hopefully it makes sense to the person who asked the question. Now the International Space Station goes around here. So if the International Space Station is here when one of these geomagnetic storms happen, it won't be too bad. But if it's here, the amount of radiation that the astronauts get exposed to is way, way, way higher than usual, and it's really, really dangerous. So it is definitely something that they need to be careful of. Unfortunately, there's no real way of protecting themselves, so they just have to kind of hope that they'll be lucky at the moment. But this is something that a lot of very intelligent people are thinking very, very carefully about at the moment. And yeah, it's hopefully going to be a problem that we'll solve in the next 20 years. Maybe you'll be the one to solve the problem, because it sure as hell ain't going to be me.
Cool, awesome question. Cool, awesome question. Any more questions? Any more questions? Okay, so I totally have one. So you said that that solar storms like stripped away Mars's atmosphere, right? But do they do anything to Earth's climate? So I know there's insurmountable evidence to show that climate change is human-driven, or the climate change impact that we're seeing right now is human-driven, and so we're doing really, really terrible things to Earth and having a really awful impact on it. But is there anything that solar storms do as well, or is there anything that they change about the climate as well?
Yes, but I can't remember what, because it's very, 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 very small. But I do remember that many years ago, I was at a conference which there was a talk about this exact thing. It was really interesting, actually, because they drew a graph and they showed it was something like this. You know, the temperature of the Earth goes like this over. It was over a period of like 1 million years or something, millions and millions of years ago. They got this data from ice core drilling and things like that. And then they did a historical recreation of the sunspot number. And I think that it did something like this, which is very interesting because those are two very similar shapes, right? But you'll notice that the change in the Earth's climate actually happens before the change in sunspot number. So we're not sure that it's actually the activity of the sun which is changing this climate. If it is, it's not the sunspots. It's something that comes before the sunspots that we don't know about yet. Or maybe the climate of the Earth is controlling how many sunspots there are on the sun. But please realize that I'm joking. That is obviously not happening. Definitely, definitely can't happen. So it's very confusing, very interesting. But I think the most interesting thing of this graph is that, you know, these are quite big temperature changes, right? But if you add on from the 1960s to the 2010s, it goes like that. So even if the sun is doing something to climate change compared to what humans are doing, it's nothing. So good question, but don't worry.
Cool. So we also had from I think cooling. Why do we only get Yeah, this is a good question. Good question. Right, and it's also another good excuse to do some more drawing. So thank you very much, whoever asked this. Oh no, I had to rub out my swag. So you'll remember that I drew a minute ago the Earth like this, right? And you'll remember that the Earth's magnetic field goes like this. Actually, you know what? I'm going to draw it slightly better. Scientific accuracy. So this is what the Earth's magnetosphere looks like. Right? And you'll remember I said that when a CME comes in from the front, comes in this way, it's like that. You get this reconnection here, and then this field line will peel back, and it will come onto the backside, and then these will reconnect here. And then the plasma can only move along these magnetic field lines. It can only go that way or that way, right? It cannot possibly go that way, for example, because there's two magnetic field lines here that are doing that. It has to follow these lines. So you'll see that when reconnection happens here, contained in all of these whole field lines always comes down here and it ends here. Always comes down here and ends here. Always comes here and ends here, even if it could happen at the front, which it doesn't. But all of the magnetic field lines on the Earth end here. And in actual fact, they spread out very slowly. And for stronger magnetic storms, you see the northern lights and the southern lights lower and lower down on the Earth. So this is a great question, because you're right. We do only see the northern lights at the poles usually, and it's because that's where all the magnetic field lines go. But for a very strong storm, you could even see it as far south as London, maybe.
Awesome. So I think we might have come to the end of the time. Does anyone have any last questions? Yeah, is that life sciences? Yeah, go for it.
Yeah. Basically, I was just wondering, in terms of the distance from the sun, is the distance from the sun like a major factor in the how the solar storm sort of surges?
Question. These kids are too good. Right. So I'll try and answer this one really quick because I know it's getting late and I'm sure you all want to go home and watch cartoons as much as I do. But this is too good of a question. So the distance from the sun. Yeah, right. Interesting. Good question. So here's the Earth and here is the magnetosphere. And this is dominated, the shape of this is dictated by how strong the solar wind is pushing into it, right? And you're right, the solar wind does get weaker the further away you get from it. And that's because, well, the sun is a circle, so here there'll be a certain amount of stuff. Here there'll be the same amount of stuff over a bigger space, so it's less dense. Here again is the same amount of stuff over an even bigger space, so it's less dense. So that means that, yeah, you're right. This pressure does get lower as you move further away. So that means if we could pick up the Earth and move it further and further away from the sun, yeah, the magnetosphere will probably balloon out a little bit like that, which is quite cool. But I think the properties of the planet, and Will actually might be a better person to answer this question because I think he works a lot with Jupiter and Saturn, things like that. The properties of the planet are actually a bit more important because, for example, let's say this is Jupiter now. Okay, so this is Jupiter, and the Earth would be about this big, let's say. Jupiter's magnetosphere is like this. Ugh. It is huge, it is enormous, and the Earth's magnetosphere is like this, you know? It's tiny, 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 tiny compared to the Earth's magnetosphere. In fact, I think the Earth's magnetosphere would fit inside Jupiter itself. I believe that's right. Will, can you confirm or deny that? I mean, it sounds crazy now that I'm saying it, but I think it really is that small. And this is just because Jupiter has much stronger processes happening inside it. Cool. The moons of Jupiter are inside the magnetosphere, so Jupiter can get the northern lights not from CMEs, but from like plasma that shoots out of one of its moons, which I think is really cool. I didn't even know about that until last week. So I hope that answered your question. I think I just got a bit excited about talking about Jupiter's magnetosphere because it's so cool.